Welcome back to the deep dive. Today, we are going to change the way you look at the world.
Hey, no pressure.
I know, we say that a lot, but I'm serious. We're looking at something that is literally all around us. It's hidden behind walls, buried under the streets.
Or sometimes it's just towering over you in these huge industrial zones.
What's
It
this?
just looks like a chaotic mess of metal spaghetti.
It really does.
Yeah,
But, what looks like chaos is actually a masterpiece of precision.
absolute precision.
Exactly. We were talking about process piping. And look, before you tune out thinking this is about, I don't know, fixing a leaky sink.
Right, this is not your weekend plumbing project.
Not at all. We are talking about the massive arterial networks that power everything. High-pressure steam, dangerous chemicals, fuel lines, the stuff that keeps the lights on.
Yeah, if residential plumbing is like playing checkers, process piping is 3D chess with very, very heavy steel pieces. The
Phew.
stakes are just completely different.
And to really get our heads around this, we pulled together a pretty interesting stack of sources today. We've got technical engineering course notes.
The real textbook stuff.
Yeah. And then we have transcripts from actual fabrication tutorials, which, spoiler alert, are way more math-heavy than I expected,
Oh, yeah.
and a really intense risk analysis report on construction safety. Plus some updates on where AI and smart tech are taking the field.
It's a great mix because it takes us from the theoretical geometry right down to the actual mud and welding sparks on a job site.
And our mission today is really just to decode this whole invisible world. I have to say, going through these sources, I was floored. I mean, I haven't thought about the Pythagorean theorem in years.
Right.
I figured it was just for, high school tests.
Mm.
But apparently it's what's keeping a refinery from blowing up.
It really is. It's applied math in the highest stakes environment you can imagine. You get the hypotenuse wrong on paper, you get a bad grade, you get it wrong here.
You have a catastrophic failure.
Exactly.
Okay, well, before we get to the life or death math, we have to start with the basics, the vocabulary. Because for most people, myself included, the words pipe and tube are.
The same thing.
Yeah, they're synonyms. You ask for a pipe, I hand you a tube. Who cares?
Oh, the engineers care. They care a lot. If you walk onto a job site and mix those two up, you're going to get some funny looks.
And maybe the wrong part, which could be dangerous.
That's the real issue.
So let's unpack this because the course material makes a huge deal out of it. It all boils down to how they're sized.
It does. And this is the part that, trips everyone up. Let's start with pipe. Pipe is defined by two things: nominal pipe size, or NPS, and something called a schedule.
Nominal being the key word there. It means in name only.
Exactly. So if you order a 2-inch pipe, you'd think something about it is 2 inches. The outside, maybe? The inside hole?
But neither is true.
Neither's true. It's just a standard name, like a 2x4 piece of wood isn't actually 2 inches by 4 inches.
Right. Okay.
Yeah. But there's a really important reason for it. In these big systems, the pipe has to fit into standard part valves, elbows, flanges. So to make that work, the outside diameter, the OD, has to stay exactly the same. No exceptions.
Okay, so a 2-inch pipe always has the same outer width, so it fits in the clamp. But what about that schedule thing? I saw schedule 40, schedule 80.
So schedule is the wall thickness. As that number goes up, from 40 to 80 or even 160, the wall of the pipe gets thicker.
To handle more pressure.
To handle way more pressure.
Mm-hmm.
A schedule 160 pipe is incredibly heavy and thick.
But wait a second. If the outside diameter has to stay the same and the wall gets thicker, where does that extra metal go?
It has to go inward.
The hole in the middle gets smaller.
Precisely. The bore shrinks. So a Schedule 80 pipe is much stronger than a Schedule 40, but it actually carries slightly less fluid because the channel is narrower.
Yeah.
You're trading flow for strength.
That's fascinating. And that's the main difference with a tube then. The notes say tubing is much more literal.
Yeah. Tubing doesn't play these weird sizing games. A tube is specified by its exact outside diameter and its wall thickness. If you order a 1 1/4 inch tube, it is exactly 1.25 inches on the outside. Period.
Whereas a 1 1/4 inch pipe
Is actually 1.660 inches on the outside.
that's almost half an inch bigger.
It's a huge difference. So if you try to connect a tube to a pipe fitting of the same size,
That's not just a bad fit, it's impossible.
totally impossible. They're from two different measurement worlds.
The sources also touched on how these things are actually made. The big distinction was seamless versus ERW.
Yeah, and this is vital for safety depending on what's flowing through it. Seamless is kind of the gold standard. They take a solid, white-hot cylinder of steel, a billet, and they literally pierce a hole right through the center of it.
So it's one single continuous piece of metal.
Exactly. No seam, no weld line, which means there's no inherent weak point. The engineering codes give it a 100% efficiency rating.
Okay, versus ERW, which is
Eh.
electric resistance welded.
Right. For that, they take a flat sheet of steel, roll it into a cylinder, and then weld that seam together.
Like rolling up a poster.
Just like that. And because there is a seam, even a perfect one, the code assumes a potential weakness there. So it usually gets a lower strength factor, maybe 85%.
And the note said you can actually spot this in the real world.
You can. If you look closely at industrial pipes, you'll see a stencil painted on the side. Type S is seamless. Type E is electric resistance welded.
And I'm guessing if you're pumping something toxic and flammable, you want type S.
You definitely want type S. You do not want a zipper on a pipe carrying acid.
Right. And speaking of danger, that brings us to the rule books.
Yeah.
The ASME codes.
The Bibles of the industry. And they say they're written in blood because usually a rule only gets added after something went wrong and somebody got hurt.
The two big ones that kept coming up were B31.1 and B31.3.
Those are the titans, yeah. B31.1 is for power piping.
So power plants.
Exactly. High pressure steam, boilers,
Mm-hmm.
anything for generating electricity. Then you have B31.3, which is process piping.
And that's the refineries, the chemical plants.
Oh, right. The process code. It has to cover a much wider range of things. Acids, solvents, all kinds of weird chemical. It's a much broader book.
And the source made a really interesting point about not cherry-picking rules between them.
Oh, absolutely not. That's a cardinal sin. Once you declare a system as, say, B31.3, you have to follow that book for everything. The safety factors, the materials, the welding procedures, it's all interconnected.
You can't just say, oh, I like this rule from the power code better, I'll use that one.
No, because you'd be compromising the integrity of the entire system. That is literally how things blow up.
Okay, so we've got our definitions, our rule book.
Uh-huh.
Now we have to actually build the thing.
Mm-hmm.
And this is where we get into those fabrication tutorial transcripts. I was expecting, welding tips.
Yeah, how to hold the torch.
Right.
Yeah.
But what I got was a master class in trigonometry.
It surprises people. They think pipe kitting is all muscle, but really it's mostly math. If you can't visualize geometry in 3D, you can't do the job.
Let's walk through the double rolling offset example. This one is fascinating. I had to read it twice to get my head around it.
It's a classic 3D puzzle. So imagine you have a pipe running along, let's say, north. You need to connect it to another pipe that's further south.
Okay.
But it's not just south. It's also lower down, and it's also shifted over to the east.
So it's moving in all three dimensions at once, south, down, and east.
Exactly. You can't just eyeball that. You have to calculate the precise diagonal line that connects those 2 points in 3D space.
And the transcript explains it using a right-angled parallelogram. They used actual numbers,
Yeah.
a 978 millimeter run south, and a 444 millimeter offset east. And they went straight to Pythagoras.
Good old a squared plus b squared equals c squared. But here's the trick. You have to do it twice. First, you calculate the diagonal on the flat horizontal plane.
Like the shadow it would cast on the floor.
Perfect analogy. So they squared the south run and the east offset, added them, took the square root, and they got a hypotenuse of 10,074 millimeters.
But that's just the flat part. The pipe also has to drop down.
Right, so now that 1074 millimeters becomes the new side A of a second triangle, a vertical one.
Oh, I see.
Side B is the vertical drop, which was 441 millimeter. You do Pythagoras again with these new numbers, and you finally get the true center-to-center length of the pipe you need to cut. In this case, 1,161 millimeters.
That is incredible. You're building a wireframe model in your head, basically.
And if you're off by even a few millimeters, that heavy steel pipe just isn't going to fit. You can't stretch it.
And it gets even more detailed. The transcript talks about cutting elbows.
Mhm.
I assumed you just buy a 90-degree elbow or a 45.
Well, what if the drawing calls for a 25-degree turn? You can't buy that. You have to cut it from a standard 90.
But where do you make the cut? It's a curve. You can't use a ruler.
You can't. So they have a formula, a shortcut. The transcript gave this magic number, 0.01744.
I saw that. What is that number?
It's not actually magic. It's basically pi divided by 180. It's the conversion factor to turn degrees into a linear measurement you can actually mark on the curve of the elbow.
So it's just the math hidden in a constant.
Exactly. It's a cheat code for the field. You just multiply the radius of the elbow by the degree you need times 0.01744, and boom, it tells you exactly how many millimeters to measure and mark for your cut.
That is so cool. But here's the catch, and the source was really clear on this. You do all that math, you get your length,
Yeah.
say it's 1,000 millimeters, You do not cut the pipe to 1,000 millimeters
No. If you do that, you've just ruined an expensive piece of steel.
because you have to account for the gap.
The fit-up gap. This is non-negotiable. When you put two pieces of pipe together to weld them, you don't butt them up tight against each other. You have to leave a space.
Usually 3 or 4 millimeters. Why? I would think touching would be stronger.
You'd think so, but with welding, you need penetration. That little gap lets the molten metal flow all the way through to the inside surface of the pipe, the root of the weld.
For a full-strength bond.
Yes. If they were touching, you'd only weld the outside. The inside would be a weak spot, a crack waiting to happen under pressure.
So the final math for the pipe cutter is total calculated length minus the fittings, minus the gaps.
And if you have 5 fittings in a row, forgetting those 3-millimeter gaps means your pipe is suddenly 15 millimeters too long, and the bolt holes on the end won't line up.
And now you have a huge delay because of a tiny math error.
A very expensive delay.
So all of this complexity has to be communicated clearly, and that brings us to the isometric drawings.
The map.
The map. Looking at one in the notes, it's disorienting at first.
It is. It uses 30-degree angles to give a 3D feel on a 2D page. The most important thing on that drawing, as the source says, is the north arrow.
Right. You have to imagine yourself standing in the center of a compass. You have to orient yourself to the real world.
Exactly. And then you have all the symbols, like those little triangles.
The slope triangles. I saw one that said 1.100. What does that mean?
It means for every 100 units of horizontal run, the pipe has to drop by 1 unit. So for every 100 meters, it drops 1 meter.
And why is that slope so important?
Gravity. You almost never want a perfectly flat pipe because you need liquids to drain. If it's flat, stuff pools and causes corrosion. But if the slope is too steep, the liquid runs away too fast and leaves all the solids behind.
Which causes clogs.
Exactly. So that 1.100 ratio is often that perfect Goldilocks zone for drainage.
And the engineer has to verify all the elevations. The source showed an example. Started 20,800 millimeters, dropped 343. The new elevation must be 20,457.
It sounds like simple subtraction. But imagine a plant with thousands of pipes weaving through each other. If your math is off, you might run your pipe right through a steel beam, or worse, another pipe.
Okay, so we've done the math, drawn the map. Now we have to actually build it. And this is where we get to that risk analysis paper. And this part's a bit scary.
It's a healthy dose of reality. The math is clean. The job site is not.
They use a risk matrix. Probability times consequence.
Yeah.
And the report says that basic tasks like pipe welding and lifting start with a risk score of 12, which is high risk.
And you cannot work at a 12. It's unacceptable. The entire point of the safety plan is to get that number down before anyone even picks up a tool.
So what are the big hazards? The paper lists swing hazards as a major one.
That's from a crane or an excavator. As it rotates, the operator has blind spots. Anyone who walks inside that swing radius can be hit with incredible force. They call it the invisible circle of death.
That's a chilling phrase. And the ground itself is a hazard. Unstable ground.
Imagine lifting a 10-ton pipe spool. If the ground under the crane support gives way even a little bit, that load can swing wildly out of control.
Then there are the welding hazards. The arc light. I didn't realize how bad the light itself is.
It's not just bright, it's intense ultraviolet radiation. It gives your eyeball a sunburn. It can cause permanent damage really fast. That's why you see those welding screens up everywhere.
It's not just for Starks, it's to protect other people's eyes.
Right?
So how do they get that risk score down from a 12 to a moderate 6 or a low 3?
It's always a layered approach. You have administrative controls, like getting a hot work permit to prove you've checked for flammable gas.
And the role of the spotter or the rigger seemed critical for lifting.
Yes. The rule is, one person gives signals, only one. If you have 3 people waving at the crane operator, they get confused. That's when accidents happen.
And finally, PPE. The report mentioned high-impact gloves for pinch points.
Right, because when you're lining up 2 heavy steel flanges, if that pipe shifts, it acts like a giant pair of scissors. Your fingers don't stand a chance without proper protection.
So we've gone from design to safety. Now let's look forward a bit with these podcast excerpts about industry trends. It feels like technology is finally catching up here.
It is. For a long time, it was a very traditional industry.
One of the things mentioned was AI in distribution. A company like supplyhouse.com using AI to help contractors find parts faster.
And speed is everything when a plant is down. A pipe bursts, you're losing thousands of dollars a minute. You can't wait 2 days to figure out which gasket you need.
And the components themselves are getting smarter. Xylem's smart pumps and this Hydrovar X thing.
Yeah, this is the big shift from dumb iron to intelligence systems. A standard pump is just on or off. A smart pump knows how much pressure is needed, it talks to the building, and it can even warn you before it fails by listening to its own vibrations.
So the pipe system is getting a nervous system.
That's a great way to put it.
But despite all this new tech, the sources all highlighted one massive problem: the skills gap.
The elephant in the room, they call the gray tsunami, the generation of experts, the people who can do that double rolling offset math in their heads, they're all retiring.
And the new generation.
They're great with the tech, but they often lack that deep hands-on experience. They know the software, but they might not have felt the heat of the weld.
The source from Odie and Bradford White said the solution isn't just hiring people, it's technical training.
Exactly. You can't just hand someone a welder and say, go.
Yeah.
Manufacturers are having to partner with trade schools to try and pass on that knowledge before it's gone. Because if you get the math wrong or the safety wrong, the consequences are just too high.
It really brings it all full circle. We started by defining the steel itself.
Pipe versus tube, seamless versus welded.
We walked through Pythagoras to figure out how to make it fit in three-dimensional space.
Yeah.
We looked at the maps, the isometrics, and then the extreme safety needed to build it.
And every single step is governed by a code, a calculation, or a safety protocol. Nothing is left to chance.
So what does all this mean for us, for the listener?
It means that the comfort and safety of your modern life, the gas in your car, the clean water you drink, it all relies on this hidden army of people who are completely obsessed with precision.
It's that precision that sticks with me. And I think that's the thought to leave everyone with. We live in a messy, chaotic world, but in process piping, there is such a thing as a perfect fit.
The tolerance.
The tolerance, that 3-millimeter gap. The difference between a system working for 50 years or failing catastrophically can be just 3 millimeters of space, filled with molten metal, calculated by trigonometry.
It's a reminder that these huge industrial feats are really just millions of tiny, precise calculations, all held together by welds.
Couldn't have said it better myself. Thanks for diving in with us today.
My pleasure.
And next time you see one of those industrial plants, maybe give a little nod to the math that's holding it all together. We'll see you on the next Deep Dive.